In this series of videos, we are going to briefly review two of the methods we've already learned for representing permutations in SN, and we're also going to introduce a new method of representing permutations in the symmetric group, which is writing a permutation as a product of transpositions. So let's begin with one of the methods that we've already covered so far. So this is writing a permutation in tabular form. So whenever we're working with permutation groups, there are lots of different ways to represent a permutation F. And the way that we choose to represent this permutation depends on what we want to do with it. So very early on when we study permutation groups, perhaps the first thing that we do is represent a permutation in tabular form. It kind of encompasses the most information, gives you the easiest, most basic way of thinking about a permutation. And it also has the benefit that it makes inverses very easy to compute. So let's do an example with that. Suppose that we've taken a permutation, which we're going to call f of n, and we're representing it tabularly in this way. So we've got the numbers n, in this example, 1 through 6, written across the top of our table, and then we've got what the function f of n does to each of those numbers written in the bottom row of the table. So this permutation sends 1 to 6, 2 to 5, 3 to 4, 4 to 1, 5 to 2, and 6 to 3. If we want to go ahead and compute the inverse of this permutation f, which is something we often want to do inside of groups, all we have to do is we label the columns n and f inverse of n, but what we did to obtain this table representation for f inverse is we've just switched the rows, interchanged them here. So this 1, 2, 3, 4, 5, 6 is now along the bottom here, and this output f of n, what was formerly the output, is now the input here. Right, so we've just interchanged the two rows of this table, and we now have a tabular representation for f inverse. However, the way that I've done it, I've simply just interchanged these two. Now I don't have the numbers in the row for n in increasing order, which is standardly what we want to do, but that's an easy enough change. All we have to do now is, if we want to have the 1 in the first spot, we'll take this column, which has the 1 and the 4, and we'll just shift that off to the beginning, and then we'll find the 2 here, the 2 and the 5, and we'll shift that next. And when we're done all sorted, we have a very nice standard tabular representation with the numbers n, 1 through 6 along the top of the row, and f inverse in the second row right here. Again, taking inverses in permutation groups is something that we often want to do, and that is perhaps easiest done when you have a permutation written in tabular form. Now, after we discussed and did some examples with writing permutations in tabular form, we moved on to often writing permutations in disjoint cycle notation. Now this has a couple of benefits, and in fact I think this is the most common way to represent elements of SN, is in disjoint cycle notation. It has the benefit that it's a little bit more condensed than the tabular form, but it's also very easy to compute powers of a permutation when they're written in disjoint cycle notation. It's also very easy to compute the order of a group element when it's written in disjoint cycle notation. So for example, suppose we have a permutation f and it's written in the following way. It sends 1 to 4 and 4 to 5 and 5 back to 1. Then the permutation goes on. It sends 2 to 7, 7 to 8, 8 to 3, and 3 back to 2. And last but not least, it takes 9 and 12 and it interchanges those two numbers. And there may, in fact, there are other numbers that the function f maps, since we typically look at the numbers 1 through n, and I don't have all of them listed here, but anything that isn't written down, we implicitly assume gets mapped to itself under the function f. Now, what we notice is that when we look at f here, that I haven't used any of the numbers 1 through 12 more than once. So this is disjoint. This cycle 145 talks about 145, and neither 1, 4, nor 5 is mentioned anywhere thereafter. The same with all the rest of the numbers. And when you've gone and written a permutation in this disjoint cycle notation, we have the this nice lemma that helps us compute the power of a permutation very easily. So the lemma says that suppose f is a permutation and that it's written in disjoint cycle notation. So that's an important hypothesis of the lemma. Suppose f is written in disjoint cycle notation. Then we can compute the order of f by just computing the least common multiple of the cycle lengths. So if we go back to our specific example, we checked that F really was written in disjoint cycle notation. The cycles really and truly were disjoint. So computing the order of F is as simple as computing the least common multiple of the numbers 3, 4, and 2, which is a pretty simple thing to do, and we see that that's 12. Now, those were the two methods of representing permutations that we've already done a few examples with. The one that I really want to introduce in this collection of videos is representing a permutation as what's called a product of transpositions. So suppose that we have a permutation F and it belongs to Sn, then it can be, the fact is, it can be written as a product of, and this is important, often not disjoint, two cycles. So a two cycle, a cycle that just has two numbers in it, sends 1 to 2 and 2 back to 1, for example. A two cycle is also known as a transposition. You can call it by either thing, a two cycle or a transposition, but from here on out I'll most likely be calling a two cycle a transposition. And what I'd like to do is prove a few things. I'm asserting that this can be done. I'm asserting that any permutation can be written as a product of transpositions. The first thing that I want to do is I want to give an example of how we would go ahead and do that. If we're given a permutation in perhaps disjoint cycle notation, how would we write it as a product of transpositions? And after we've done that example, we'll go ahead and we'll prove that in fact every permutation in Sn can be written as a product of transpositions. So here's our example. Let's suppose that we have a permutation, a really easy permutation. It sends 1 to 2, 2 to 3, and 3 back to 1. Let's see if we can find values of A and B for which we can take F and write it as the transposition 1, 2 multiplied by the transposition AB. So let's see if we can figure out what A and B would have to be in order to make this equality true. 1, 2, 3 is equal to 1, 2 AB. And then we'll move on to just a slightly harder example. We'll take the permutation G, which is 1, 2, 3, 4 in disjoint cycle notation, and let's see if we can write it as a product of three transpositions, 1, 2, AB, and CD. And from there, hopefully we'll see a pattern we'll be able to generalize, and this will lead us into this more general theorem. So let's start with F, the smallest of these two, and let's suppose that we have this product of transpositions, 1, 2, and AB, and we want that product of transpositions to be equal to this cycle 1, 2, 3. So we want to send 1 to 2, 2 to 3, and 3 back to 1. So for starters, if we're looking at 1, 2, AB, if we want that to send 1 to 2, then that's already taken care of in the first transposition. 1 gets sent to 2. So the easiest way to ensure that that happens is to just have neither A or B mention the number 2. And when that's done, 1 will go to 2, 2 won't be mentioned in AB, and we can begin writing 1, 2, AB in disjoint cycle form as 1, 2. From there, what we need to do is figure out where 2 gets mapped to continue writing things in disjoint cycle notation. So we return back to this 1, 2, AB, and we notice that in the first transposition here, the number 2 gets mapped to 1. Now, we don't want the number 2 to get mapped to 1. We want the number 2 ultimately to be mapped to 3. So if 2 gets mapped to 1 in the first permutation, in this first transposition, then what we need is we need the number 1, as it sort of moves on into the permutation AB, we need 1 to be mapped to 3 inside this permutation, and then that will lead to 2 ultimately being mapped to 3 when we combine these two elements. But we're dealing with just a transposition here. So if AB needs to send 1 to 3, then that's exactly what it's going to do. It's going to send 1 to 3 and 3 back to 1. And we check that 1, 2, 1, 3, when we multiply those two cycles together, that's equal to the transposition 1, 2, 3. Now I should mention that, in abstract algebra textbooks and which way you read your multiplication in permutation groups is up in the air. You can either read left to right because that's the way you want all group operations to work, or you can read right to left because it's function composition. I choose to go with reading left to right, so I would compute 1, 2, 1, 3 as 1 gets mapped to 2, 2 is no longer mentioned, so ultimately 1 gets mapped to 2. Then I would say 2 gets mapped to 1 and 1 gets mapped to 3, so ultimately 2 goes to 3. And then we just double check. 3 isn't mentioned in the first transposition, so 3 gets mapped to 3. And then when we move on to the second transposition, 3 gets mapped to 1, so ultimately 3 gets mapped to 1. So I read left to right, not right to left, in determining where my elements go. Now, if you play a similar game, and I think you should just to convince yourself, I've given away the answer for the harder permutation G here. If we want to take 1, 2, 3, 4 written in disjoint cycle form and write it as a product of 3 transpositions, the easiest way to do that is to write it as 1, 2 times 1, 3 times 1, 4. And you can at least check very easily for yourself, reading left to right, of course, that 1, 2, 1, 3, 1, 4 is indeed equal to 1, 2, 3, 4 in disjoint cycle notation. Now the last thing that I want to do in this first video is now go back and use that example as motivation to prove the following lemma, which is that every permutation f in Sn, as long as n is greater than or equal to 2, so transpositions make sense, can be written as a product of transpositions. Now, the first thing that we need to do is we need to note what happens with a fixed point. So we need to think about any permutation we could possibly have, and many permutations have fixed points, points that just get mapped to themselves in disjoint cycle notation. Since n is greater than or equal to 2, we know we have at least 2 different numbers inside of, we're looking at the symmetric group on at least 2 letters, so we can pick 2 numbers that are not equal to each other, a and b. And you can write a fixed point as AB times BA. That is, any transposition is its own inverse, so if we send A to B and then B right back to A, this has the effect of just sending A to A. And similarly, if we send B to A and A to B, then B will get mapped to B. So the cheater's way of taking a fixed point and writing it as a product of transpositions, which we said we had to do, is to just write it as one transposition and then the same transposition over again. So that takes care of what do we do if we have a fixed point inside an arbitrary permutation. And the next thing we have to consider is what if we have an n cycle where n is greater than or equal to 2. So you have some number c1 followed by some number c2, and you go on until you get to some number cn. Using the motivation from the last example, so recalling we had 1, 2, 3, 4, we had written that as the transpositions 1 goes to 2, 1 goes to 3, and 1 goes to 4. Using that mentality and just not using the specific numbers 1, 2, 3, and 4, we noticed that we could take an arbitrary n cycle and we could write it as a product of n transpositions, or sorry, I believe n minus 1 transpositions, and in the following way. Take the first element, which is C1, and then have that get sent to C2 and end that transposition. Then have the next transposition send C1 to C3. Then have the next transposition send C1 to C4. So each transposition begins with C1, the first element in the n cycle, and this last place in each transposition just goes down the rest of the list, C2, C2, C3, C4, and so on until you hit Cn. And that's one way that you can take an n cycle and write it as a product of transpositions. So if we believe that we can take a fixed point and we can write it as a product of transpositions, and we can take an n cycle and write it as a product of transpositions, then we can start out with an arbitrary permutation, which is just a collection of cycles of different lengths and fixed points. And we can just go through cycle by cycle and fixed point by fixed point and write each thing individually as a product of transpositions, and combining all of that together, you'll get a representation of this original permutation as a product of transpositions. Now it's important to take a look and think at what this lemma is saying. This lemma is saying, a lot of times in mathematics we look at both existence of something and then uniqueness of something. This lemma is not saying anything about uniqueness. We're not saying that you can write a permutation uniquely in this very specific way as a product of transpositions. We're just describing an algorithm by which you could write a permutation as a product of transpositions. So we're not asserting that there's only one way to do it, we're just giving one way of doing it and saying that accomplishes that we are able to do this. The very next thing that we need to do is talk about, is there some sort of uniqueness, and what can we say about it? That's what we'll be looking at in the second video.